In this next video, we'll be covering once more concavity in terms of a radical rational function. So in this particular example, we've already, in a previous video, covered the derivative. So I'm going to go ahead and rewrite the derivative of this function in its most simplified form. So for us to do increasing and decreasing, we had to take the derivative, and we got something that looks something like this. Now again, this is its most simplified form in terms of us working with it mathematically, algebraically, but what we want to do is we want to find the concave up and the concave down of this function. To do so, we need to actually take the second derivative. So for us to take the second derivative of this function, we actually have to have this looking slightly differently. Now I'm going to rewrite this so I see 4/3 times the 2x minus 8 to the power of a negative 1/3. Again, I write it that way so that this constant can simply just carry down through the derivative, and I can simply just take the derivative of this function as it is. So again, first step is to always take the first derivative. Second step is always take the second derivative. To take the second derivative, we might have to manipulate what our simplified version was. So now, one more time, the derivative of a constant times any function is that constant times the derivative of that function. So I'm simply going to carry down that 4/3, and then the derivative of this thing right here, I'm going to go ahead and multiply by the exponent, carrying it down, leaving the inside alone, and then subtract 1 from the exponent. So I now have a negative 4/3 as my exponent. Don't forget that this is a chain rule, and I therefore need to take the derivative of the inside and multiply by that. This provides me now with my second derivative, which again I'm going to clean up just like I cleaned up the first derivative. I'm going to take this 2 and this 4, put it on top. Don't forget the negative, I'll put that up there too. The 3 times the 3 in the denominator, that's going to be a 9 in the bottom. And then I'm going to have this whole thing to the negative exponent, which is the same thing as that whole thing to a positive exponent in the denominator. Now if you wanted to clean this up anymore, you could have go ahead and written it like this, which I have a third root of 2x minus 8 to the 4th power. You'll notice then that this bottom stuff here is always going to be a positive number. Again, because it's the 4th root of anything, the 4th power of anything, will always spit back a positive number. That means 9 times a positive is a positive, and on top I have a negative 8. So what this should tell you is just by looking at this information right here, that this thing is always going to be less than 0. So let's go ahead and test some values. Again, I want to go ahead and find out where the derivative equals to 0 and where, the second derivative does not exist. Those are my so-called critical point values. In this case, it's never going to equal to 0 because the top can't happen, so that one's out. Now, where does the second derivative not exist? Well, if you look at this down in here, 4. If I plug in 2x minus 8 equals to 0, that means x is equal to 4. So we do actually have a critical point. So there is a location where we could have a not necessarily less than 0. So let's go ahead and test this just to make sure, however, that on the interval where 4 is, I have negative infinity to 4, and I have 4 to infinity. I'm going to have a test value. The test value being, let's say, 0 here and say 5 here. And I'm going to have the second derivative function. And when I plug in 0, I'm going to have negative to the 4th power, which is positive, 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 and then spits back a negative. And then when I plug in 5, I get 10 minus 8 is 2. 2 to the 4th power is positive. Negative on top is negative. So now, one more time. This is true, except where the second derivative does not exist. So you'll notice if we didn't check for critical points in this example, you telling me that it's going to be less than 0 from negative infinity to infinity would actually be wrong. So we have to be very careful. Ensure again, you still check where it's equal to 0. You still check where the derivative doesn't exist. X equals 4 is a point where the derivative doesn't exist. So I will say that we have the original function is concave, and again, negative derivative, concave down on both those cases. But if I were to write out my intervals for concave down and concave up, I'd have to say none for concave up, but concave down will be from negative infinity to 4 and 4 to infinity, because 4 cannot be included, because 4 cannot be plugged into the second derivative function. That ends that problem.